Go.
Hi, everyone. We're back again today for the fifth of eight little sections with Paul Violet's work, papers that I wrote. And we've got Jeremy, Amber, and Brendan. Brendan is going to read to us today, and we're going to go through another 10 pages. So the last time we talked about actually, I can't remember what we were talking about last time, so we'll just jump into it. Yeah. So if you want to go ahead, Brandon, you can start reading and I'll
Yeah.
kind of follow along.
Okay, this is page 21 of Eddie's notes on subquantum kinetics and anti-gravity. Okay, so I'll start now. In this out of spec high voltage operating region, the tube's characteristics would have become highly nonlinear and prone to develop what is called the longitudinal sawtooth instability, which causes electrons circulating in the magnetron
Magnetron, yeah.
to begin to bunch up into clusters,
Charge clusters, sounds like.
transforming the tube's normal sine wave output into a series of sawtooth spikes.
Yeah, so that's really, really important. We're operating them out of spec at very high voltage. Also, but the longitudinal sawtooth versus the sine wave, but they bunch up in clusters, so that sounds like charge clusters to me, right?
Okay, I'll continue reading.
Yeah.
By operating the tubes beyond their specifications, the Skyvolt team was apparently attempting to produce microwaves having a maximally abrupt rise time, hence a very nonlinear negative potential onset curve.
Very important, negative potential. Yeah.
This in turn would have maximized the electrogravitic thrust that these waves were producing. The subquantum kinetics electrogravitic relation indicates that such
Waveforms.
waveforms would have been repulsive.
Yeah.
The entire setup, which included high voltage power
Power.
generators, microwave generators, waveguide ducts, and wave shaping resonators, required a building the size of a barn. I required a
Yeah,
sorry,
that was right.
required
Yeah.
a
A
building the
building
size of a barn.
inside.
The conical test beam was projected upward and made to buoy a test vehicle. What's that word? B-U-O-Y?
Yeah.
Buoy
Yeah.
a test vehicle
Yeah.
that had a concave bottom inside.
Concave bottom wide enough to receive the beam.
A concave bottom wide enough to receive the beam. He disclosed that this concave portion was made from a ceramic similar to
Corningware.
Sorry, was that Corningware?
Corningware. Yep. So this is really important because what they're talking about here is they're talking about a lens. So it's a lens that's tuned to a very specific frequency in the microwave region, and it doesn't have to be translucent because it's microwaves. So it looks like Corningware, literally.
Although Corningware is optically opaque, it is partially transparent to microwaves. Thus, given the proper shape, it
yeah.
could be made to act as a microwave lens, which would look not necessarily, which would look similar
Similar.
to an optical lens, but would not necessarily be optically transparent. Such a lens could be made out of paraffin, ceramic, or glass. The important thing is that it be made of a material having the proper permittivity and permeability. So the Skyvault team could have
Use the
used the craft ceramic bottom as a lens to refract the microwaves that were being beamed up to it. However, for a diverging microwave beam, one would expect that they would have used a converging lens to bring the waves to a focus inside the craft. One wonders whether this concave ceramic was actually a meta material that was engineered to have a negative index of refraction.
very important, very, very important. And this next thing is ultra important again, too.
One characteristic of left-handed negative index materials is that they have a concave shape in order to bring a microwave
Beam.
a microwave beam to focus the other side of the lens. The Skyvault team began replacing their magnetrons with solid-state oscillators called gun diodes.
That's important. Sorry. Yeah.
That were much more reliable. The gun diodes normally require less than a watt of power to operate. They were able to engineer special high power gun diodes suitable to their project. These were able to produce up to 10,000 watts of microwave power and functioned over a frequency range of 1 to 500 gigahertz. By the way, Amber, are you recording the sound or the video as well?
I'd be both.
Yeah, I'm recording both.
Okay,
Yeah.
okay. More efficient devices called impact ionization avalanche transit time diodes, impact diodes. Impact, what does it say? Is that
Yeah, IMPATT diodes, yeah, impact.
Were developed that were capable of higher microwave power outputs.
It's gallium, I think, nitrate.
Gallium nitrate gun diodes, frequencies as high as 3,000 gigahertz, have been achieved
Commercially
available, have been achieved commercially. Available gun diodes have efficiencies of up to 2 to 5%. Impact are about 10%. Magnetrons are 60%. Crystal of gallium arsenide would spontaneously oscillate at microwave frequencies. When a sufficiently high DC voltage was applied to either side of it, gallium arsenide exhibits a negative resistance when
very
subjected.
important. That is really important again. Sorry, Brandon.
Yep. gallium arsenide exhibits a negative resistance when subjected to an electric field of greater than 3000 volts per centimeter. Other substances found to exhibit this oscillating effect are indium phosphide,
Yep.
cadmium telluride, zinc selenide, and what's that one there?
I think Wirtz light gallium.
Quartzite gallium nitrate. Latter materials oscillate when biased at higher potential of about 150 kilovolts per centimeter. It is possible for civilians to produce gun diodes that
Purchase gun diodes.
It is possible for civilians to purchase gun diodes that produce up to 30 watts of power. One defense aerospace avionics distributor had shipped out an experimental 1040 gigahertz 300 micron oscillator of a rated 70, is that 70? 70 kilowatts.
Yeah, or 40. I think it might say 40
kilowatts.
Yeah.
Called microwave oscillators. The high power gun diode used in Skyvolt vehicle, like the magnetron, was mounted in a waveguide box. This had an opening of one end and dimensions that matched the diode's oscillatory characteristics. The conduit's length was made to equal some multiple of the wavelength of the microwaves emitted from the gun diode, so that the waves would resonantly reinforce one another as they reflected back and forth along the length of the waveguide.
So essentially, we're setting up a soliton, a standing wave that bounces back and forth. So the dimensions have to be very critically tuned to the frequencies that they're looking for, right?
Okay, this resonance world
would increase the.
So this resonance would increase the beam's voltage. They were designed to operate in the range of a few 100,000 volts to 1 million volts. Commercially available gun diodes operate at 5 to 100 volts DC, direct current. Parametric amplifier, a device commonly used. Is that right? Parametric.
Yeah, parametric.
A device commonly used by microwave engineers to boost signal strength. The parametric amplifier consists of a cavity containing a nonlinear medium, such as a varactor capacitor diode.
Yeah.
The beam to be amplified is allowed to enter and exit the amplifier cavity through a part, and while in the cavity, it passes through the diode where it energizes.
Its energy.
Where its energy is pumped up as the result of the action of a second microwave beam called the pump beam.
Yeah, that's important.
Pump beam has a frequency twice
Of the
mains oscillator frequency. Oscillator frequency so the frequency twice the mains oscillator beam.
Yep.
So oscillator beam, and is oriented at 90 degrees.
Yeah, 90
to
degrees to
the mains beam, so as not to directly interact with it. Parametric amplifiers are capable to amplify a beam energy from 100 to 1000 times. 10 kilowatt microwave oscillator signal could be boosted to operate at a 10 megawatt microwave beam. One interesting thing about parametric amplifiers is that their energy output can greatly exceed their energy input.
Mhm.
The amount of this over unity output
Yeah.
versus input depends on the type of nonlinear medium and its response, and its per response in the frequency range used. The magnetic resonance amplifier is an example of one such amplifier that operates in the audio frequency range rather than at microwave frequencies. Based on theories of John Keeley, it uses a high K dielectric such as barium titanate capacitor hooked in series with a coil wound around a barium ferrite ceramic magnetic core. What's that? But by exciting it,
yeah.
at a frequency around 8,000
Yeah, 8,000 to
11,000 hertz. This excitation frequency is chosen to be 3 times the resonance frequency, that is 3 octaves, 9 harmonics above resonance. Power is drawn from the oscillating ferrite core through a secondary winding that is connected to a bridge rectifier. One such device, built and tested by American researchers Joel McLean and Norman Wote, achieved a power output of 2.75 watts for an input of
0.7.
0.7 watts, or an over unity ratio of about 4. At resonance, the voltage across the tank circuit ranged up to 1,000 volts when excited with a 30-volt AC or alternating current pump signal. Even higher outputs than this have been reported for parametric amplifiers in audio range.
Last page.
Okay, for example, in 1949, Oblensky built a parametric, I think it's Obolensky built a parametric amplifier that used a super
Permalloy.
perm alloy ferrite as its nonlinear medium, and was able to achieve an over unity ratio of about 1,000,000 to 1 when he
Wow.
pumped it at frequencies of 60 to 400 hertz. It is possible to draw off
Some
of the energy surplus in the main beam that is being amplified, and to recycle this power, the parametric excitation process. So to recycle this power, the parametric excitation process. This could be done by connecting the pump beam waveguide tube to a fourth part on the circular cavity. The circular
circular
mains. The circular would contain not only the fundamental frequency of the main beam, but also its harmonics.
Yeah.
So by making the length of this connecting waveguide equal to an odd number of half wavelengths of the main beam's second harmonic frequency, the fundamental frequency would be blocked, and
and just the second harmonic would pass through.
And just the second harmonic would pass through to the parametric amplifier.
Yep.
As the fundamental frequency becomes more intense, so would its harmonics, and a greater amount of power would become available in the second harmonic for parametric excitation. As a result, to what's that word? As a result, its beam as a result, its beam intensity will progressively increase.
Yep.
So just
back of the last page.
did you want to make any comments about that, Eddie?
Just that what's really important is like we're talking about a pump beam coming in, a secondary pump beam, and everything has to be set up properly for the proper wavelengths, so it's all very, very critically calculated. And no, we can just carry on. This page, I noticed the writing is even getting worse, so let's see if we can get through it.
Another page.
Yeah, the back of the page. It's the last page. So go back to
that one there.
25. Go back to 25 and then go to the back of it.
Okay.
There's one more page.
That one there.
Let's see. Can you make it bigger? Yeah, that's the one. Yeah.
So previously it was that one we just did.
Yeah, and then it's the
That's
back of page 25. Yeah.
Making such an amplifier work properly so that it is able to boost the wattage of the microwave beam without are we still recording? We're still recording, okay.
Yeah.
Of the microwave beam without, excuse me, without blowing the amplifier apart is a quite tricky
it is quite tricky. It requires
it's quite tricky. It requires a
incorporating
requires incorporating a fast-acting servo control that automatically changes the phase of the
phase of the pump beam frequency.
Pump beam frequency when the amplifier output power level gets too high. This would
squelch
the amplification process and
halt
the exponential rise in energy production.
Yeah.
Don just describes two types of anti-gravity microwave systems. The simpler version called homodyne.
Yeah.
What's that one there?
Yeah, homodyne used the same
conduits for both transmitting and receiving. He commented that this system suffered from a lack of range since its microwave beam typically targeted at no more than 30 miles.
Yeah.
The second type of configuration, on which he called the 1 micron X unity, used separate transmitting and receiving antenna. It originally operated in the X microwave band, which exerts from 8 to 12, which extends from 8 to 12 gigahertz phase conjugate mirror. When illuminated,
with a radar pulse.
When illuminated with a radar pulse echo coming in from the pulse target, it produced an outgoing microwave pulse that so let me just read that bit again. When illuminated with a radar pulse echo coming in from
the
target, it produces an outgoing microwave that exactly retraces the path of the incoming target echo signal.
Yeah. So, and this was all a part of this was Skyvault, which was just experiments that they did. And you know, this is mostly all drawn from Paul's work on secrets of anti-gravity propulsion. So there's a lot of references back to that book. If people are looking to further understand this, then they should actually definitely get that book and this book as well, which Brandon sent from London. So I'm very excited to have, because these were very, very expensive on the internet to buy them. And there was a few of them left. But what's really fantastic, this is the 3rd edition. Brandon is just finishing the 6th edition, and we're going to have it printed in a hard copy with color pictures. So that's going to be fantastic. Hey, Brandon. Really looking forward to that, definitely. So that kind of wraps up the last, or the next 10 pages. So we have three more of these, because this is 5 that's done now. So there'll be 3 more of these, and then we'll get through all of the papers essentially. So I really appreciate you reading to us again today, and for everyone to be here. And I guess we could probably stop the recording at this point, and we can chat some more. Yeah. So thanks again, and We'll see.